Hey, how's it going?
All right.
That time of semester, everyone's tired.
It's a long day. Morning.
Oh dang,
That was fun.
it's always not fun.
Yeah.
Hello, Dr. Chan, can you hear me?
Yep, I can hear you.
Sounds good.
Okay, it's 7 o'clock. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Doing good. Okay. All right, so today is activity 7, and so this is our second to last activity. And so we have this one and then one more next week. Okay. And just like we discussed on Monday, the subject for this activity is modal and vibration analysis. Okay, and so what we're going to be doing is I have this CAD model, so it's a gearbox. And so we're going to be doing primarily modal analysis on this. I don't have harmonic analysis as actually part of this activity. I kind of forgot about that as we were going to the lecture on Monday. But if you want, we can take a look at harmonic analysis later today too. I just have to remember how to do it. Okay. Okay. All right. And so that is the plan for today. So we're just doing the activity today. Any questions I can answer before we get started? Okay. All right. So let's go ahead and get started. And so just like we normally do, you can go ahead and go to our Canvas site. You can go to the activity page, you can download the specifications, and most importantly, you can download the CAD file. Okay. So this gearbox file here, this was made in ANSYS, it was made in Design Modeler, and so it should upload without any issues. Okay. And we're going to be following basically our We're going to be following through the instructions on the specifications. Okay. All right, so the first thing we're going to do is we're going to start with a static structural, just because we've kind of always done that. And then what we're going to do later is we're going to link our modal analysis to the static structural. Okay. All right, so let's go ahead and click and drag the static structural over here. Okay. So let's go ahead and import our gearbox geometry. And so go ahead and import it just like we normally do. Okay. And then what we're also going to do here is we're going to add some material properties. Okay, so not only are we going to change the materials for the initial activities, but you're going to need some additional materials from later on in the activity as well. Okay, so let's go ahead and double click on engineering data. So just like we normally do for this. Okay, and I'm going to go to engineering data sources, and then let's go ahead and go to general materials, wherever it is.
And this is the static structural?
Yes, static structural. Yeah.
Thank you.
Okay. All right, so it looks like I accidentally closed the window for this, but let me go ahead and bring it back. Okay. All right, so what you're going to do is you're going to click on. Okay, let me do this again. Okay, so let's go to engineering data sources and let's go ahead and click on general materials, and then what you should see is window here for the general materials. Okay, so we're going to add two here. So we're going to add gray cast iron, and we're also going to add stainless steel. So stainless steel is actually very similar to structural steel. Of course, the main difference in reality is that stainless steel has, a surface treatment to make it stainless, but we're going to add it to this one. Okay, and so you should have three materials when it's all said and done. So you should have structural steel. So that is that's kind of our main one. You should have gray cast iron, and you should have stainless steel. Okay, so we're going to use both gray cast iron and stainless steel for this project. Okay. All right, any questions on this so far? Okay. All right, so let's go ahead and go back to the project. So we go ahead and close engineering data. Okay. And let's go ahead and open up ANSYS Mechanical. So let's go ahead and double click on model here. And we can bring up ANSYS Mechanical. All right. And so when you open up ANSYS Mechanical, this is the part, okay? And if you go over to the geometry side, you can see here we have three parts to our assembly. So we have one part for the housing, one part for the flange, and another part for the base, okay? So first thing you should notice is that the housing here has a question mark, okay? The reason the housing has a question mark is because if you actually look at it, it might be easier if I turn off the base. So let me go ahead and hide this for a second. And so if you look at the housing geometry, you can see here that it's very thin. Okay? And so what we've done already, or what ANSYS has done, or the person who made this geometry has done, is that they've turned this housing part into a shell. Okay, and so naturally this part here at a very small thickness, and so they've just turned it to a shell to make it easy for us. Okay. But because it's a shell, remember, one thing that shells always need is they need a thickness, right? And so even though, visually, you don't see any thickness associated with this part, in reality, this part does have a thickness. And so for this project, what we're going to do is we're going to assign a thickness here. And the thickness we're going to assign is 3 millimeters. So if you want, you can change the units here to millimeters to just make your life a little bit easier, okay? But 3 millimeters is also the same thing as 0.003 meters. And so, you can do either one. Okay. But we want to make sure we assign a thickness of 3 millimeters to this. Okay. And then for the material properties for the housing, we're going to make the material for the housing stainless steel. Okay. And so in summary, the housing part, you're going to make two changes here. So you're going to assign a thickness of 3 millimeters, and you're going to assign a material of stainless steel. Okay. For the two other parts, for the flange and the base, for the flange, we're going to change its material to gray cast iron. And then for the base, we're also going to change this to gray cast iron as well. Okay. All right. So kind of in summary, housing is stainless steel and a thickness of 3 millimeters. Okay. And for the flange, we have cast iron. And then for the base, we also have cast iron. Okay. As I write that in serial killer font. All right. Any questions on this? This is just the property assignment for the parts. Okay. Yeah. Yeah. So for the housing, it's stainless steel. And then for the flange and the base, those are both cast iron. Okay. And we're good. All right. So let me go ahead and clear this. Okay. All right. The next place we're going to go is to the connections. Okay. And so we need to define our connections here. And so remember, whenever you have a shell type geometry, or whenever you modify the geometry for shells and beams, ANSYS kind of automatically deletes a lot of the connections that we have. Okay. And so if you go to the contact regions here, we only have one actually. And so the only contact region that we have is between the housing and the flange. Okay. Okay. And so we need to add one additional contact region here between the housing and the base. Okay, so let's go ahead and right click on contacts. Let's go ahead and insert a manual contact group. Okay. Then what we're going to do is we're going to select two things. So we're going to select the bottom edge of the housing and then the top face of the base. Okay. Okay, so let's go ahead and do that. All right. And so for the contact here, we're going to specify the bottom edge of the housing. And so you might have to use Control and click to get all four of these edges. Okay. Okay. And then for the target, we're going to switch to surface mode and click on the top edge of that face. Okay.
Can I see you do it again, please? Sorry about that.
Sure. And so for the contact, you're going to do the bottom four edges of the housing. So let me go ahead and select those again. And so it's going to be this one, this one, this one, and this one. Okay. So basically all four edges of the housing that are in contact with the base. And so we want to make sure you select those four. You're going to make that the contact. Okay. And then for the target, you're going to click on the top face of the base. And so that's going to be the thing that's contacting the housing. Okay, so you're going to click on the top face of the base, and you're going to set that to be the target. Okay.
Thank you.
Yep. Right. And remember, so I chose these in a very particular order. And so if you try to switch these, and so if you try to make the contact the four edges, and you try to make the target you try to make the target the four edges and the contact the face, you'll actually run into an error. So let me show you. Okay. And so if I flip these, and so if I make it so that the target is the four edges and the contact is the base here, okay, this is giving us an error. So ANSYS is telling us that there's an issue with this thing. Okay. Remember, when we talked about nonlinearities, that when you choose these, the target, what you choose to be the target is almost always going to be the bigger of the two, or the one with the more surface area compared to the two. Okay. And so since the base here, we're selecting a whole surface, that is a lot bigger than the four edges we're selecting for the housing. Okay. And so you want to make sure that the target is actually the face and not the edges. Okay. But if you have it switched, you can always just right click it and click on flip contact and target, and then it'll flip those two. So that's kind of a nice feature in ANSYS. But if you're ever kind of working on ANSYS, maybe for your project or something, and you're having an issue defining the contacts, that may be something you could consider just to swap those and see if that gets rid of that area. Okay. All right. So next step, we're going to mesh. Okay. And the good thing for this is that we actually don't need that much of a mesh. And so let's go ahead and just generate the default mesh here. Okay, let's see what that looks like. All right, so I didn't apply any meshing settings, and so this is what it looks like. So this actually looks pretty good already. So, we're not really doing a lot of stress analysis here. We're mostly focusing on the resonant frequencies, and so we actually don't need that much of a mesh. But just like always, feel free to kind of tinker with the mesh. You can add settings if you want, but for now, I'm just gonna roll with the default mesh. Okay. All right, so now we're going to add loads. Okay, so first thing we're going to add is our fixed constraint. Okay, let's go ahead and right click on static structural. Let's go ahead and insert, and let's go ahead and add a fixed support. Okay, and the location of the fixed support is going to be the bottom of the base, because that's where the gearbox is going to attach to whatever it attaches to. Okay. So now we fix the model. So technically that's all we need for modal analysis. But we're going to add some loads to this as well, just to kind of see some pre-stress. Okay, but we're going to use a new type of load. So we've never used this load before, but it may be useful to you, in your project. So I want to kind of show you what it is. Okay. All right. So the load we're going to add is something called a bearing load. All right, so a bearing load is a special kind of force. And so the way this works is that it's a load that you typically apply on kind of the interior surface of a hole. Okay, because if you look at this gearbox, we have kind of these four holes on the flange, right? And so the assumption is that inside what goes inside these flanges here are rods, right? So if you can imagine, a rod is kind of going through here. Okay. Maybe not all the way through like that, but I'm trying to draw with a mouse here. Okay. And the way that load is being applied is that this rod is going to be pulled. Right? So this rod may be pulled in this direction here. And so of course that force is going to translate to the gearbox on this surface here. Okay. And so one thing we can do is that we can actually apply kind of a normal force load here. Okay. And so if we apply the force in a normal way, and so we go right click here, we go to force, okay? We can do that. And so there's, ANSYS is not going to stop you from doing that. But the argument is that in those cases, a regular force would be not as accurate, okay? Because what happens, so when you apply kind of a regular force boundary condition or a regular pressure boundary condition, what ANSYS does is that it takes that force and then it evenly distributes it throughout this entire surface, right? And so this part of the surface will be experiencing the same amount of force as this side, okay? It would all have the same magnitude in the same direction, but all parts of the surface would be kind of acting the same way, okay? For kind of a bearing hole like this, that's usually not the most accurate thing, because if you have a rod that's kind of pulling on this, right? And so let me kind of view it from this direction here, okay? And so let's say that we have a rod kind of inserted into this flange, okay? And let's say that rod is being pulled this way, okay? So something is pulling on the rod, and then that rod is kind of transmitting a force to your gearbox, okay? And so when you have a rod that's being pulled this way, right? Then what's going to happen is that you're going to have a higher concentration of force here, okay? On the part that's actually making contact with the rod as it's being pulled in that direction versus this side right here, okay? Actually, this side experiences very little force because the rod is being pulled away from that surface. Okay, and so the idea with the bearing load is that we can apply the load on kind of a circular surface like this, and most of the load, instead of being evenly distributed throughout the entire surface, most of the load is going to be concentrated on the part where a theoretical rod would be kind of contacting that there. Okay, and so that's the load we're going to use in this case. Okay, and so we're going to apply 4 forces. So we're going to apply 4 bearing loads, and they're going to be on each side of the basically each flange hole that we have. Okay, and so the actual magnitudes of the forces are actually given in the project's specifications. Let me kind of go ahead and show you. So if you look at this figure here, so this figure here shows you, I've gone ahead and labeled all four of the holes here. So we have A, B, C, and D. Okay. And so the forces you're going to apply are going to be according to this table here. Okay. And so in part A, you're going to apply a load that has a magnitude of 16,000 newtons in the X direction, 30,000 newtons in the Y direction, and 16,000 newtons in the Z direction. Okay. All right, so I'll go ahead and let you guys fill that in, but just make sure that you use bearing loads for all four of the loads.
It's in the inside surface.
Inside surface, yes. Yeah. Yeah, so let me show you one just to kind of show. All right, so we have one bearing load here. Okay. So I'm going to target the inside surface of this flange here. So we're going to go ahead and hit apply. Okay. Apply the load according to components. Okay, and then I'm going to insert the X, Y, and Z components according to what's on the project specs. And so for A, we have a 16,000 Newton load in the X direction. So this is going to be 16,000. Okay. In the Y direction, what do we have? 30,000. And then in the Z direction, I think we also had 16,000. Okay. All right, so go ahead and apply that to all of the holes. Okay. So one thing you can do just to kind of keep it organized, because we're adding quite a bit of loads here. You can label them just to kind of remind you what surfaces they're being applied. Okay, so I have bearing load A, bearing load B, bearing load C, bearing load D. Okay. And then once you're done adding all those loads, go ahead and insert the total deformation and the equivalent stress. Okay. And then try running the simulation as it is. Okay.
Where is the fixed support? Is that the bottom?
Yes, the fixed support's on the bottom.
Okay. I got that error too.
Yeah, we'll discuss in a second. You should get this there, but we'll kind of discuss. We need to discuss kind of why you're getting that. So is everyone able to apply the four bearing loads as they are? Okay. All right. And so if you try to run the simulation as it is, you're going to get an error. Okay. And so if you read the text for the error, what you should see is that what it tells you is that you have a bearing load that has an axial component. Okay. They said this is not allowed. And so if an axial component is desired, create a separate force node in order to apply that axial component. And so this is one of the rare times where the error message is actually very descriptive and actually very helpful. Okay. All right. So what does this mean? Okay. And so, let's go back to kind of our definition for the bearing load, right? And so the bearing load basically assumes that the rod is being pulled in a certain direction, and we're concentrating a lot of that force on that surface. Okay. That's only true if your force is kind of in plane with the bearing hole. Okay. And so we have kind of a nice case here because our flanges are actually aligned perfectly with the z-axis, right? And so all of our flanges here, or all the holes, are pointed in the z direction. Okay. And so what that error is telling us is that we can only have bearing loads or bearing forces that are in the XY plane. Okay. We can't have any out of plane bearing forces, right? Because technically speaking, if we look at bearing load A, right? If we look at bearing load A, you can see we have a component of 16,000 newtons in the z direction, right? And so that's going out of the plane of the bearing. Right? And so what that 16,000 Newton component here represents is that it represents a frictional force. And so there's like some frictional force. And so if the rod was being pushed into the bearing load or bearing pole or pushed out of it, then there is a reaction force that's going to occur. Okay. But what ANSYS is telling us is that we can't actually have an out of plane force for the bearing load. Okay, so what we're going to do, so we have two such forces here. So we have a force on bearing A and a force on bearing D. Okay, so we're going to eliminate the z component. Okay, so for bearing load A, we're going to make the z component 0, and for bearing load D, we're going to make the z component 0. Okay, and so what we're going to do instead is we're going to apply it as a normal force. Okay, all right, so we're going to add two more forces to this, and so let me go ahead and right-click static structural, and we're going to insert a force. Okay. So this force right here is going to be axial force A. Okay. And so just like on surface A, we're going to select the inner surface of bearing A. Okay. We're going to apply that or define this in terms of components. And we're going to set the z component of this equal to 16,000. Okay. And then we're going to do the same thing for surface D. Okay, so surface D, we're going to put an additional force. We're going to select surface D right here. Okay. Let me rename this axial force D. Okay. And then we're going to find this in components. And the component for the surface D is a minus 16,000 newtons in the Z direction. Okay. All right. And so if you rerun the simulation, where you basically get rid of all the axial components of the bearing force and move them to a regular force, you should be able to get the following results. Okay, so you should have a deformation field that looks like this. It looks scary because we have the auto scaling on. Okay, let me go ahead and turn that off just so you can see kind of a more true scale. So the result here is 55x. So let's go ahead and do true scale. Right. And so you should get deformation about 0.74 millimeters and an equivalent stress equal to about 180 megapascal. Okay.
If we get I had a question. If we get like a equivalent stress that's like 4 numbers higher, that's fine, right?
Oh yeah. There's always going to be a little bit of noise to these measurements. Yeah.
Okay, thank you.
What was the question of it?
Can you show the force again?
Yeah. So axial force A is going to be on this hole right here. So if you're kind of viewing it from the top, it's the bottom left one, and then axial force D is going to be on the top right.
And what are the?
Yeah. So for axial force A is going to be 16,000 in the Z direction, and then axial force D is a minus 16,000 in the Z
Are
direction.
you applying those on the inner part?
Yeah, the inner part. Yeah. So same surfaces as the bearing plates. All right, so is everyone able to get the static structural results as they are? Yeah, question.
How did you get the true view?
Oh, yes. Yeah, so people, yeah, it's confusing because if you notice, one thing ANSYS is, it's always going to auto scale the results. And so it makes your deformations look way scarier than it actually is. This is the bottom here. And so to change that scaling, you're going to go to, you're going to make sure you click on either the total deformation or the equivalent stress. Okay. And then you're going to come to the top banner here and click on result. And then under result, there is kind of a drop-down menu here for the scale. And so I think the auto scale is like 55x. And so if you want it to be just 1x, you can set it to true scale, which is just 1. So it's right here.
I got an error.
What was the error you got?
One or more contact regions have contact shell faces or target shell face set to program.
So that sounds like an issue with your connections. So when you created this extra contact region here, did you set it to be the 4 edges and the 1 face?
Yes.
So the 4 edges of the housing, and then the 1 face is the top side of the base.
Correct.
Okay.
There's that other contact region there.
Yes.
You have, what should I do with that? Nothing.
So that one was created by default. So that one should stay there. Maybe try creating the contact region again one more time. So again, go ahead and delete the one that you made manually, and then just make it again. And yeah, you want to make sure that there's a green check mark next to the connection after. All right, any other
check mark.
questions? Green check mark, and then go ahead and run the simulation.
I'm still getting the same thing.
Getting the same message too, but the results.
Oh, so you're Chris, are you able to get results, but you're just getting a warning message for that?
Yeah.
Okay, let's go ahead and move on from it for now. If it's a warning, then it's hopefully it doesn't affect things too much. It could be something so I'm working with the 2021 version here just because we're a little bit behind in updating these computers. But that may be a warning they added in kind of the newest version of ANSYS. But I think we should be able to proceed. So as long as you're getting the total deformation results that look somewhat similar to this, and then the equivalent stress looks similar to this, let's go ahead and move on for now, and then we can investigate that warning message after. Yeah.
Okay.
Yeah.
You went on the
true scale. Yeah. And so you're going to go to result. And so you want to make sure you click on either total deformation or equivalent stress. You're going to click on result. And then up here, there is a drop-down menu where you can choose. And so the default is auto scale. And so you can change it to true scale right there. Result. So in order to get the result to show up here, you have to click on either total deformation or equivalent stress. Oh, okay. Were you able to get the scaling? Okay. Wait.
Under outline or it's all certain.
So when you try clicking on solution A6 and then go to, well, it's not under solution. It should be under one of these results. You got it? Okay, good. Okay, any other questions on this part here? Okay, all right, so let's go ahead and close this. And so, that was just the static structural part. So now we're ready to move on to modal analysis. Okay, so let's go back to Workbench here. Okay. And so what we're going to do is we're going to take our static structural and we're going to link it together with modal analysis. Okay. And so for that, we're going to click on, back on Workbench here. You're going to go on the toolbox on the left-hand side, and you're going to locate modal. And so it's kind of right above modal analysis. Okay. Okay. Or modal acoustics. And so we're going to click on modal here. and we're going to click and drag it on top of model. Okay. And so what that's going to do is that it's going to link the geometry for your, it's going to link the geometry for your static structural, and it's going to link the meshing and the boundary conditions as well. So let's go ahead and link that. Okay. And so after you do that, you should see something like this. And so you should see a modal analysis, but there should be these links that occur between your static structural analysis and the modal analysis. Okay. So with those links set up, let's go ahead and double click on setup here. And so what that's going to do is going to reopen ANSYS Mechanical. Okay. And so it's going to seem like, you know, we stepped out and we only just stepped back in. Okay. But the main thing here is that, you know, we've added this extra thing here called modal B5. Okay. And so we still have all our static structural stuff. So we still have static structural A5, but now we have this modal B5 as well. Okay. Okay. So we're going to run the modal analysis in kind of two different modes. And so on the one hand, we're going to try without any pre-stress. And so we're not going to apply any of the loads, and we're going to see what our resonant frequencies are in that case. Okay. And then we're going to try it with the loads, and we're going to see how that changes our results. Okay. Okay. So first we're going to try without any of the loads. So this is going to be an unstressed modal analysis, right? And so even though we're not applying the loads, we still have to apply our fixed support. Okay. So let's go ahead and right click on modal B5. So let's go ahead and add a fixed support. Okay. And so we're going to fix the bearing, the gearbox in the same place as our static structural. But right now we're not inheriting the boundary condition for static structure. So that's why we kind of have to do this again. Okay. So let's go ahead and add our fixed support. We're going to click on the bottom surface of the gearbox. We're going to hit apply. Okay.
Professor, is there any way we can transfer all the loads?
Yeah, we'll do that next. And so the way that we're going to transfer it is through this pre-stress right here.
Okay.
But we're gonna see what it looks like without any of the loads first. Yeah. Yeah. And so, you know, when we have no pre-stress, that means we're not inheriting any of these at all, including the fixed support. And so we re-add the fixed support just to kind of make sure that we don't get any rigid body motion. Okay. And so after you add your fixed support, you know, that's basically it. So let's go ahead and hit solve. And so ANSYS is going to solve this. It shouldn't take too long. Okay. Right. And so once the solution is complete, you should see a green check mark next to solution B6. Okay. So let's go ahead and click that. Okay. All right. And so then what you should see is that all the results here are on the bottom. Okay. All right. And so there are a couple plots that you can see here. I think the one that's more useful is the tabular data. Okay. And so what those are showing you is that these are the resonant frequencies, or these are the natural frequencies of this gearbox if it were fixed on the plot. Okay. So our first harmonic mode has a frequency of about 318.82 hertz. Our second harmonic mode has a frequency of about 429.82 hertz. And the third and the fourth and the fifth and so on and so on. Okay. If you're not getting my exact numbers, it's okay. So there's always going to be some variance in these. And so as long as you're kind of in the same ballpark as these, then that's fine. Okay. Okay. Was everyone able to get the resonant frequencies from the modal analysis? Okay. So yeah, it's very quick. And so, you know, that's basically it to modal analysis. And so a lot of times, you know, this is kind of this table right here is kind of what you're most interested in. And so for most modal analyses, we can kind of stop right here. Okay. But let me show you a couple other cool things.
Question mark screenshot, is that the?
So I'm going to show you how to do the mode shapes. And so the mode shapes is primarily what I'm looking for. Yeah. Yeah. All right. And so if you remember on Monday, we also talked about this idea that, you know, when you excite the structure at different frequencies, you're going to get different resonant modes or different resonant deformations. Okay. And so to see what those shapes look like, let's go ahead and highlight all of these frequencies here. Okay. And then I'm going to right click this. And then I'm going to click on this option here for create mode shape results. Okay. And so what this is going to do is it's going to create 6 new results, okay, 6 new entries for our results, which show us what the resonant modes are going to look like. Okay, so the first harmonic mode, second, third, fourth. Okay. Because remember, for modal analysis, there's kind of 2 parts to it. And so on the one hand, it's useful or it's good to know what the resonant frequencies are. But after you solve for the resonant frequencies, you also want to know, what the resonance is actually going to look like. So how is your part going to fail in that case? Okay. Okay, so I'm going to click on this create mode shape results. Okay. And so you can see here that it's created 6 total deformations, right? And so in order to evaluate these, we're going to click on solve. Okay. And so it should be fairly fast. Right? And so what we can do now is we can click on each of these deformation plots, and they're going to show us what the harmonic modes look like. Okay. Okay, so let's click on the first one here just to kind of see. Right. And so you can see here that this is our first harmonic mode. Okay. So actually, let me rename this just so to make it a bit more clear. So this first harmonic. Okay. And so if you were to excite this structure at a frequency of 318 hertz, okay, then this is kind of the deformation that you can expect. And if you want to kind of see it kind of oscillating in action, you can click on this play button. Okay. And this play button will kind of show you exactly how the resonance is going to occur. Okay. So you can see here that the deformation is kind of oscillating between these two. Okay. And so that's kind of what you can expect. Right. And so for a gearbox, this is especially relevant because what you have for a gearbox is that you have kind of shafts that go inside these bearings, and those shafts are going to be spinning, right? And so what this is saying is that if your shaft is spinning at a frequency of 318.82 hertz, or either something in that range, you're going to get resonance in this way here. Okay. So was everyone able to get the mode shape for the first harmonic mode? Okay. All right. And so remember, a word of caution here. So remember, we talked about this on Monday too. When you're viewing these harmonic modes, the way ANSYS shows it to you is as a deformation field, right? And so you can see here that it has units of millimeters, and it even has a magnitude. Right? Remember, these numbers are meaningless. And so, they don't actually tell you the magnitude of the deformation. Okay. These numbers are only there just to give you a relative sense to show you, which parts are going to deform more than the others. But you're not actually going to get 12.11 millimeters of deformation in the red zones. Okay. Because remember, the actual deformation that you get depends on the magnitude of the loading that you actually put in. Okay?
Dr. John.
Yes.
I know you probably already said this, and this is redundant, but so I'm looking at that chart that has the mode, right?
Yeah.
So mode 1 is where resonance occurs.
You're going to get resonance at all 6 of these, and so you're going to get resonance at all of them. But the first one is usually the one that you worry about because usually when you have oscillating loads, you usually approach from the bottom up, and so you usually don't have,
because it's going to break at the lowest number first, obviously.
Usually, yes. And so usually you don't approach resonance from the top down. So you don't have something that spins really fast and slows down to reach resonance.
No, I see.
You have something that starts slow and then ramps up to what the resonant frequency is. So, the first resonant mode here is probably the most important one. That's the one that people are probably concerned with.
Yeah, that's the one that's going to be approached first.
Exactly. But you technically still get resonance at all these other ones.
Yeah, all those values are bad.
Yes. Yeah. But usually you're not going to get into this range over here. Usually. There are circumstances where you can, but for the most part, you're interested in the first one. And usually the first one is going to have the highest magnitude of resonance as well. And so usually as you get to the higher resonant modes,
yeah, I know what you mean by that.
Yeah, the amplitude kind of dies down once you get to
resonance. Sounds good, sir.
All right. Any other questions on this? Okay. All right, so this is the stress-free configuration. And so if you look at the activity specifications, you can see here that I want you to show the mode shapes. And so I call them deformation fields here because ANSYS called them deformation fields. Okay. So I want you to show me all 6 modes for the stress-free. Okay. And so for when you're preparing your activity report, I want you to go through, first harmonic mode, second harmonic mode, third one, fourth one, fifth one, and sixth one. Okay. And I want you to show me, screenshots of what these look like, and get a good angle where you can actually see all the deformations. Okay. Okay, so that's the first part of problem 2. Okay. The second part of problem 2 is I want you to show me the same thing, but with the pre-stress. Okay. Okay, so let's see how to do that. And so if you remember on Monday, one thing that we talked about that's going to affect your resonant modes is the presence of any kinds of loads on your structure. Okay. Okay. And so to inherit all the loads, and so one thing you can do, of course, you can insert all the boundary conditions again, but kind of the best way to do this is to kind of inherit all the loads from your static structure. Okay. Okay. And so the way you do that is you're going to go to your modal B5, and then under this setting here called pre-stress, you're going to change the pre-stress environment to static structural. Okay. And so what that's going to do is that it's going to inherit all of your loads and all of your supports from your static structural analysis. Okay. Okay. But you should see one thing. So after you change the pre-stress environment to static structural, what you should see now is that your fixed support kind of has this blue question. Okay. Because now this fixed support here is redundant. Because if you look back at our static structural, we have this fixed support already, and so we don't need another one. So we can go ahead and suppress this, okay? And then let's go ahead and run the analysis again. Keep in mind, and so let's kind of remember. Let me write it down here so we can remember. Our first harmonic mode in the stress-free one was about 318 hertz, 318.8. Okay. Let's see what the first harmonic frequency or the first resonant frequency is going to be after we insert this this pre-stress. Okay. You can delete it, but then if you're going to switch back and forth between pre-stress and no pre-stress, you can just suppress it. You can just kind of turn it on and off. Yeah. You can't have 2, and so when you inherit the static structural, that means you're also inheriting this fixed support up here too. Oh, you mean back in Workbench right here? Can you have like two modes?
Right there, so like the solution B5.
Yeah.
If you click that, right click down on B5.
Yeah. Oh, solution.
Model.
Yeah.
No,
Mhm.
model, yeah. Right click. Duplicate.
Yeah. Oh, yeah. You can do that. So you can have kind of a stressed and a pre.
Separate.
Yeah, you can have them separate as well. Yeah. Mhm.
In that case, if I have it like that, I just delete it.
Exactly. Yeah. Okay. Okay. And so let's look at the resonant frequencies here. Okay. And you can see here we do have a change. Okay. And so when we add the pre-stress to our model, we can see that the resonant frequency changed from 318.8 to 318.4. And so, not that big of a difference. Okay. Actually, what you should see is you should probably actually see more differences in kind of the higher order modes, more so than the first one. But you can see here that it doesn't make that big of a difference. And that kind of is consistent with kind of what we discussed on Monday as well. And so on Monday, what we said was that kind of the biggest driver or the biggest contributing factor to the resonant frequencies is going to be the geometry, not so much the loads. So the loads, you can see it does make a difference, but it's a very, very small, almost minuscule, almost kind of meaningless difference. Okay. All right. Any questions on this? Okay. All right, and so that's modal analysis right there. And so there's not that much more to talk about for that. Okay, so let me go over the rest of the activity for you. Okay. And so what I want you to do for the rest of the activity is I want you to kind of experiment with the different factors and then see and observe how that actually changes your natural frequencies. Okay. And so for problem 3, I want you to change the material properties. Okay? And so I want you to do two different alternate scenarios here, right? And so what we've just done, so I would consider this kind of the base scenario, okay? And so for the change of material properties, I want you to do 2 alternate scenarios. Okay? And so I want you to choose a material that's stiffer than stainless steel for the housing, okay? And then I want you to choose, and then that's going to be one scenario. And so I want you to kind of rerun the analysis and see what the resonant frequencies are for a stiffer material, okay? And then after that, I want you to choose a material that's more flexible, right? And so one that has a lower Young's modulus, and then do the same thing. And so I want you to show me all 6 deformation fields and then tell me how the resonant frequencies changed, okay? And then for problem 4, I want you to change the geometry. So, you know, same thing here. And so this here I would consider to be kind of the baseline for the geometry. Okay. And so I want you to do 2 alternate scenarios here. So I want you to do one adjustment where you add material to the geometry. Okay. And then I want you to do another configuration where you take away material from the geometry. Okay. And then and you can do that however you want. And then same thing here. So I want you to show me how the natural frequencies are going to change relative to these 2, you know, changes to the geometry, as well as show me the 6 kind of mode deformation fields. Okay. So one easy way, so I'll give you a hint on how to do problem 4. So one easy way to add and subtract geometry is you can change the stiffness of the housing. And so that's kind of another reason why I chose this geometry here, is because it already automatically has a shell part of the geometry. And so one easy way to add and subtract geometry is you can adjust the thickness of the geometry. Okay. And so to add material, you can just make the thickness thicker. To take it away, you just make the thickness less, and then just rerun the results. So you don't actually have to change any dimensions. Okay. Okay. So that's problem 4. And then problem 5, I want you to do vibration design. Okay. So here I want you to, you know, kind of put yourself in the shoes of a typical kind of structural engineer. Okay. And I want you to basically make changes to the geometry or make changes to the material properties to basically change the natural frequencies. Okay. And so, you know, in our default configuration, you know, our natural frequency was around 300. It was around 320. Okay. I want you to change the design of this gearbox so the natural frequency is around 200 instead. Okay. And so if you're anywhere within this range, and so, you know, this is kind of tight here. So if you're anywhere within the range of like, you know, 180 to 220 hertz. Okay. And so as long as you're kind of anywhere within that range, you know, for problem 5, then that's fine. That's half that I'm happy with them. Okay. So you don't have to hit 200 on the nose, but you know, as long as you're kind of in that range, then that's good. Okay. And so after you do problems 3 and 4, after those, you should get a sense of kind of, you know, how the geometry affects the natural frequency, how the material property changes the natural frequency. And so you can do any combination of material and geometry changes to kind of get you within this range. Okay. All right. And then problem 6, as usual, is just kind of a summary. And so just write just a quick 1-page summary of this report. Okay. All right. Any questions on this? Okay. All right. So we have about 25 minutes left in class. And so I'll let you guys get started on the activity report. And so if you haven't finished up problem 2, where you kind of compare the stress-free and the pre-stress, definitely go ahead and do that. And then go ahead and get started on problems 3 and 4 as well. Okay. So during this time, I'll be making the rounds. And so if you have questions on the activity, we'll go ahead and look at the warning that people are seeing regarding the connection. And if you have any questions, you can come ask. But besides that, you know, the activity is basically done. And so, you know, if you would rather kind of finish up this activity kind of on your own time, I don't have anything more of value to say today. And so you can go ahead and take off. So thank you guys for coming today. You know, we're quickly getting to the end of the semester. You know, so I always appreciate you guys coming to lecture. And so if you guys are taking off, so hope you guys have a good weekend, and I will see you on Monday.
Thank you, Dr. Chang.
Thanks. Okay, so let's I'm gonna look at someone's computer here regarding that error, Chris, and then I'll kind of report back to you. Okay. If you're still here. Okay.
I had just a quick question.
Sure.
Would this count as one of the ANSYS extra, like on the part of the final report?
Yep.
You know how to do like an extra step?
Yep, this counts. And so this is one of the extra features that you can apply towards your final project.
Okay, thank you, Professor. Have a great rest of your week.
Thanks, you too.
Thank you.
You got your. More reasons.
With the edge versus like that. Yeah.
Usually when you do program control, it should fix this, and then you let the program control that there's doing. Right. Probably referring to one of these. These things. But a lot of these are so advanced. And usually you set it to program control and actually picks the right thing for you. You can see for all of these that there's so many. There's so many different. Yeah. But I think it's kind of it shouldn't cause an issue, especially with kind of a simple project like this. I think the average user wouldn't know what to pick these. I don't know if it's like something that is just kind of a bug that they have, because this hasn't shown up in the previous version. It's only in 20. And so I wonder if it's a bug that's just kind of recently come to their attention. They're kind of working on it scores, but I don't think it should kind of. The value is sort of. Yeah. Okay. Yeah, I wouldn't worry about it. So, oh, it's not even a warning. It's just. Okay. Yeah, I think it should be. But yeah, if you run into issues with it, just let me know. All right. Yeah. All right, Chris, are you still there?
Yes, I'm still here. I heard,
Okay.
It sounds like it's just nothing I need to worry about.
Yeah. I don't think it's anything to be worried about. I think what's happened is that because there's if you look at kind of the all the settings under contact, and so I can show you on my screen too, actually. And so if we look at the contacts here, there are a lot of settings here that are program controlled, right? And so the idea, the idea with having things being program controlled is so that ANSYS kind of has the flexibility to kind of choose what's best for a given situation. Because there's a lot of settings here that are kind of pretty advanced that most users wouldn't would normally just not touch at all. So I think what's happening is that there might be a bug in their code right now where they're having an issue with one of these program controlled. Because usually when you have something that's program controlled like this, there's some kind of algorithm that ANSYS is running to kind of determine which setting is the best. And so I think what's happening is that they probably have a bug right now that's with their algorithm where it's not choosing the best thing in some kind of very niche situations. But I think for our case, because we're working with fairly simple stuff, because we're in a classroom setting, I don't think this is going to affect us. And so it's probably there's probably some very, very edge, very, very niche cases where this program control is not behaving well. And so that's why they throw that warning message. But I think for us, I think there's nothing to worry about.
Okay.
Yeah, that's what it sounds like to me, just kind of reading it from So whenever you see the default, then you click so so maybe the default. It's interesting though, that it shows on a smaller mesh. I mean, that's where I was. Because the plant is a base that the base of the. Yeah. Why don't you change my fleet one day? And for this activity, it doesn't matter. In most, for most cases, that have more control. But most times you're not going to run. I think there's just this. Yes. Yeah, so there actually is a random vibration mode. There is right here. Oh, so I've actually only seen one. It's meant to simulate that thing. It's random vibration. Yeah. So my understanding is that now. Beyond that, I don't know exactly. But you can probably look up some. And then the random vibration. The random vibration will tell you. Either random vibration, so I know random vibration that something similar is going to be this one response. That's the one I kind of talked about at the end of the lecture. That one you could build off of. That one's a bit different. More just going through all of the design and seeing all that kind of smooth. So random, I think, is important. Yeah, random from those provided. All right, cool. No, it's gonna be, yeah, I could, we're getting near the end of the semester. This is already kind of. I decided not to. Okay. Yeah, that's fine. Yeah, you but definitely. Right? So you want to make it part of your money. Yeah. I definitely. I'll see it when it comes. Yeah. It's all a matter of time. So that's fine. Yeah, but this we don't get about. Yeah. You guys have a commercial license. Trying to get it. Okay. And trying to convince our management to. It's a hard sell. Yeah. Well, right now we have the SolidWorks one, which doesn't give you the amount of control. Maybe just like a couple licenses. Yeah, I know Pomo likes. He's a lot better than the. Yeah, there's definitely more options. Yeah. So in terms of in terms of like consumer management, three strategies for three. Yeah. Is the variation. Reject colonization. Say it like the variation. No. So the differences are going to be gone here. Because it affects, because when you add the pre-stress, basically what you're doing, so you open up. Yeah, but if you open up the static structural results, you will see that the equivalent stress is going to be different in each part of the model. And so the point by point pre-stress, the point by point equivalent stress, that affects kind of the natural frequencies. And so how all those different parts are interacting with all that kind of contribute. For the lower order modes, it affected a certain way, but for the higher order modes, it's affected.
So do I notice in terms of knowledge that different modes, for example, like the second mode, which had here. Stress bond,
Yeah.
Third.
Yeah.
This higher than third. So it's very bond.
Yeah, it's pretty non. Are you talking about the mode shapes, or are you looking at the stress shape?
Some of them. So they, but I was just under the impression.
Yeah.
For some of these cases.
Yeah.
The. Later than. Previous volume.
Oh, okay, I see, that can still happen, and so you can try out. That can still happen, although, it's kind of more common to happen on all shift. The shift may not be all the same, but yeah, typically you all kind of say. Possibly. Something.
But in terms of the. Vibration design.
Yeah.
So. In terms of. Like altering the design of. In terms of the natural frequencies that we're looking for. Our deal is just that the only one that we.
It's only the first one, only the first one. It's gonna be really hard to get all of them.
Is there some sort of optimization?
You could do that. Position on top of the whole. Yeah, and so, let's see. A way of getting this out. Definitely think there would be, that's something that we definitely want to offer.
In like okay, additional.
Maybe, yeah, because you definitely need a way to make that first harmonic frequency parameter. Then that's something like, and certainly, I mean, that would be kind of the first thing I would try to offer.
Like a system. I think. Never knew ANSYS did Six Sigma.
Six Sigma?
Yeah,
What's that?
like optimization, it's more of the efficiency structure or something.
Oh, okay.
That's usually used in there.
Oh, okay, yeah, ANSYS, there's a lot of features in ANSYS. It's a very full featured software. So there's a lot of stuff in there. I think, I've been teaching the classes here for, I guess, almost 5 years now, but I think I still only know maybe like 10 or 15% of ANSYS. There's so much stuff in it. And even more stuff in like the commercial version too, that we don't even have access to.
Oh, wow.
It's only the student version, yeah. I mean, it's pretty good, right? I mean, even for a free student version, they package a lot in here, so there's a lot we can still do. Yeah,
The only bad part is like never really see how powerful
right,
it is because of like that
the limitation.
limitation.
Yeah.
because of fluence. Like,
Yeah.
one of my main problems with my midterm project was that's I practically spent like percent of the time.
Yeah.
It's just trying to refine
Mm.
mesh.
Yeah.
And trying to find a mesh that actually can be computed.
Yeah.
A point where difference in millimeter.
Yeah.
Shifted the number of elements or almost doubled the number of elements.
Yeah. That's kind of how it is. Yeah, that's definitely the most frustrating part, but that's also how they get you to buy your software too. Because they're not giving you the student version out of the kindness of they want you to, they want to sell you the software or convince your company to buy the software. Yeah.
In terms of like design exploration, is there like a difference between direct optimization and swan surface optimization?
They're different algorithms. So the direct optimization is the quicker option because what that's aiming to do is just give me the most optimal design parameters. For the response surface optimization, you're kind of asking a different question. So you're asking it to do more of like a wide search. And so not only are you trying to find the most optimal solution, you're trying to basically map out, all the different changes. So if you have 3 parameters, say for instance, and so for the optimization surface, what you're saying is that, as you're trying to look at all the relationships. So if you change this parameter and this parameter, then you can expect your outputs to kind of go up and down like this. And so it gives you it lets you more better explore the design space rather than just giving you a single answer. Yeah. It's a lot more expensive, but sometimes you need that for more complicated cases.
In terms of, like, for example, this gearbox to successfully design a geometry that is within the ranges of all modes, would you use?
If you're interested in just like, because when you're doing an optimization, what you're interested in is, give me 3 like input parameters. So maybe like the thickness of the housing, maybe the diameters of the bearings, and maybe the width of the base or something like that. And so for direct optimization, what you can say is that, I want all the frequencies to be less than this, or the range of frequencies to be this. And if all you're interested in is just give me the most optimal values of the housing thickness, the diameter, and the thickness, that's what direct optimization is for. But if you're interested in saying, I'm not really sure exactly kind of what I want to choose for these, but I want to better understand, like, if I change the diameter, this is going to occur. If I change both the diameter and the thickness, then this is going to occur. And it's going to occur in kind of this way. Then that's what you would use as a response surface. Yeah.
Sure. Have you ever seen Brave Firefly?
Yeah.
We watched that this weekend.
How are you not like devastated?
Yeah.
Right?
It's awesome.
Oh yeah.
It's like gonna be scary.
Fun.
Yeah.
Yeah.
It's just how it works with the words.
Yeah.
Yeah,
It's just like, I know. Kid, man.
yep.
Yeah.
And then-
there'd be something.
We went to Little Tokyo after.
Oh, yeah?
All we can think about is like, oh no, like the characters, and I'm like, oh god,
Oh yeah.
I can't enjoy this.
Yeah. I watched that when I was in college, and like, man, that's not what I want to see before I take my finals yet. I'm just like depressed. I'm depressed for a
Hey,
week.
Professor,
Yeah. What's up?
the instructions and my simulation have some differences
Okay.
that I would like to just figure out whether I need to worry about them or not.
Sure.
So.
You want to share your screen so you can see?
So that's, you see right there,
Okay.
for
Yeah.
figure 7, the total deformation.
Yes. So this is for your static structural, right?
Yeah, this is for the static structural.
Okay.
I'm
So
trying
actually,
to,
the one I did today, actually, the deformation was lower too, but it wasn't that much lower. Let me see your stress field.
I can't tell if you're actually seeing what I've got here.
I see the document, but I don't see the. Are you back on? Are you back in ANSYS?
I'm trying to figure out what I'm doing wrong. Apparently, I don't know how to run this, so
Okay, there we go. Okay, your stress is actually pretty close, but yeah, for some reason the deformation is.
yeah. And it's a little lower because in this it's 5.9667, but the document is 0.7687. So it's a little bit, the deformation is a little smaller.
Yeah. How are your resonant frequencies? Are they kind of around 320? Okay. So these are a little bit different too, but not super different. Let me see your materials for all three parts again. Stainless steel. Okay, and then let me see the flange and the base. Huh. That's very interesting. I mean, everything else looks to be the same. I'm guessing all the loads are the same magnitudes as well. The mesh wouldn't cause that big a difference. 16,000.
I went through and made sure all of my loads were proper.
Let me see bearing load D again. And let me see bearing load C. Okay. Yeah. These are all the same. That's very interesting because let me look at my deformation results again. Yeah, it's somewhat close, but it is different still.
So is yours different from mine or different from the document?
It's different than both, but my deformation that I'm getting right now is applied to 0.74 maximum. So it's different, but not as different as yours.
Could it have something to do with the mesh?
In theory, but your mesh looks good to me, and so and the mesh wouldn't make that big a difference in the deformation anyway. Let's see.
Can't think of anything that would account for it.
Yeah.
So
Everything else.
I mean, the bottom.
So for this activity, I mean, it's I mean, the focus of this activity is mostly on the frequencies. And so your frequencies look to be the same as pretty much the same as mine.
Okay.
Actually, even yours is actually even a lot closer to the document than mine
The
were today.
document might be wrong.
Yes.
My equivalent stress is pretty close. It's like 10 off.
Right. Yeah. Yeah, usually when kind of your deformation is off that much, but your stress is still the same, kind of the first thing I would check is probably the material property. But you're using just the boxed stainless steel and the box gray cast iron. So
right,
assuming those are the same, unless they change them between versions, which is
they might have.
Let me check. Let me see your stainless steel material properties, and let me compare that with mine. I'm also looking at Young's modulus, so 1.93 E5 megapascal. Okay, that's the same. Let me see your gray cast iron. Okay, well, these say that at least these say that they're the same, but
we are working on different versions, and as you
yeah.
noticed, I had this.
Right. Yeah. Someone else had that today too.
So maybe it's an error in the code.
It could be. It could be. Yeah. So for the other student that had that error today, I didn't check and see what his deformations were. But maybe it is something to do with that. Maybe there is something with the contacts that's causing that issue. But for the sake of this activity, I wouldn't worry about it. I would just focus on just the frequencies. And, maybe, for your project or for just any future applications where you have a shell connected to a base like this, we can look at it again. But yeah, for this one, I wouldn't worry too much.
Okay. For the final,
Yep,
we're not allowed to do the same geometry. We have to do one of the others, right?
exactly. Yeah, or you can choose your own, but as long as you choose something different than your midterm project, then I'm fine with it.
But it's basically the same thing, maybe with a little more analysis.
Exactly.
Okay. I haven't been able to tackle the final because I'm working on Dr. Azazi's
Yeah,
second midterm.
I heard that is a doozy right now from other students in the class.
Yeah, he's always a doozy, but he gives us time and he lets us talk to him, which is
I
nice.
see. I see. Okay. Yeah. So when you get to working on the project, just if you have questions, just let me know.
Okay,
Mostly the same as the midterm project with just a few extra stuff.
thank you and good night.
Thanks. Have a good night. Yeah.
So for the problem number, the vibration design, is
Yes.
it okay if you just change the thickness of the housing?
Yeah. You can just make one change.
Just one change?
Yep.
That's enough.
Yeah. So if you've already gotten that just
So
from.
we keep the materials back to the original, same thing it was, and just change the thickness of the housing.
Yep,
Make
that's
sure
fine.
it comes between 190 and 110.
Yep.
That's it.
That's perfect. Yep. All right, Cole, any final questions before I wrap it up? Okay, all right, so I'm gonna close up the call, so I'll see you next week.